All right, welcome back, everybody. We're moving on to Chapter 2. Chapter 1 should have been a lot of review so far between Calculus 3 and ODEs. Finally, in Chapter 2, we're getting into some material that you've probably never seen before, but it's very closely related to material you have seen before, so it's a very slight extension. We're not really going to get into solving PDEs into Chapter 3, but once we get there in Chapter 3, we'll be using a lot of techniques that we've discovered so far. Okay, so with all that said, we're moving into section 2.1, which I'm calling tensor fields, inner and outer products. So certainly one of these names you've probably heard of before, that is the inner product. You probably know of it as the dot product or the scalar product. They all kind of mean the same thing in a lot of situations, but inner product is usually the best choice for the name. But we're adding these other ideas. We're adding tensor fields as an idea, and we're adding outer products as an idea. And tensors, if you're a physics major, a physicist, you've probably heard of tensors before. These describe forces in lots of directions at certain times, but they're actually broader than that, and we'll get into really what they are in this section. Now, fields just describe the fact that the domain, everything that's a field, when we say a vector field, scalar field, tensor field, or so on, we're describing that the domain of a map is d-dimensional for some d greater than or equal to 2. Right, so the field, the idea of the field, where did that name come from? It came from, if you're actually out in nature, which I know is a big ask of a lot of you. If you go out in nature, you're on a field, there's some grass on the field. And the idea is the field is two-dimensional. It's got some depth, and it's got some width. And so there are two dimensions which describe where I'm standing in a field. And then within the third dimension, there's actually attached to every point in the field, there's a stalk of grass, right? And so there's grass attached to every point, every 2D point on the field. And we have choices on what we can measure on the grass. We could measure the height. And the height is a number. We can measure the direction it points in. And the direction is a vector. I mean, a lot of them point up, but depending on if they're swaying to one side or another, then they're going to point slightly to the right as well as up, and slightly to deep as well as up, or something like that. You could even measure some more complicated behavior of the grass. You can measure the change between two stalks. And really it should be not between two stalks, but the change between a collection of stalks, right? The change between surrounding stalks, right? If I'm measuring the change between surrounding stalks, this would in fact be a matrix. And so there's all sorts of choices I can make on measuring these blades of grass that are sticking up from the field. And depending on what I choose to measure, I'm going to recover either a number attached to every single point on the field, right? The field gets dotted with these numbers, or I get a vector attached to every point on the field, or I get a matrix attached to every point on the field. And this is where the idea of this word fields came from. Perhaps, don't quote me on that. It makes a lot of sense to think about them that way, so I'm fairly certain that's where it came from. So we're going to get into it. Tensor fields are just kind of the general space that all of these exist in. So the simplest tensor field is called a scalar field, and this is probably the language you used in Calc 3 to describe these. So a scalar field, a number and a scalar, we can think about as the same thing. A scalar is just a number that's allowed to multiply. It's allowed to scale vectors. So a scalar field is a function whose domain, right? We care about the domain of the function. The domain is going to be a subset of a vector space. Okay, so it's going to be some d-dimensional domain, omega and rd. And we'll look at this function. We've got omega as the domain. Its output, though, the important thing is that the codomain, which is the output of the function, is a field of scalars. Okay, so scalar field and field of scalars, very confusing. Two different things. This field right here is an algebraic field, unrelated to the physical field or analytic field. Okay, so this field and that field are describing different things, which is annoying. Welcome to mathematics. But anyway, the output of this function is going to be a field of scalars, namely numbers. That's what you want to think. So the output's a number, the input is d-dimensional. So omega is some higher dimensional space. So the input, d-dimensional, output is a number. We've got some examples of scalar fields. And basically all I want you to note is that the input on these examples, there's 2 inputs there, 3 inputs there, d inputs here, whatever x is a vector in, whatever x is a vector in, those are all of the inputs, and they're more than one of them, right? They're between 2, 3, d, and whatever x is. But the outputs, right, this is a function which is combining multiple inputs together, but it combines them into a single number. You'll notice that no matter what these outputs are, the outputs have been combined. They combine all inputs into a single number. Okay, so we start with 2 numbers, we end with 1. We start with 3 numbers, we end with 1. We start with d numbers, we end with 1. Whatever that vector is in, we end up with 1 number. Whatever that vector is in, we end up with 1 number. So it's a scalar is talking about the output here being 1 number. Field talks about the input being multiple numbers. If we jump up in this whole idea of a tensor algebra, we're heading into a vector field. This is now where the domain, because it's the word field, the domain is still a subset of the vector space. So the input to my function is still d-dimensional, omega and rd, d-dimensional. Now the output is allowed to be, codomain is allowed to be another vector space. Okay, so now instead of going from a d-dimensional space to numbers, I'm going to a d-dimensional space into vectors. So output is vectors. Input is vectors. So vector to vector is a vector field. I can look at some examples of this. It's a great example. I've got 2 inputs, I've got 2 outputs. Now I've phrased the outputs in terms of a vector. This is usually the way we do it, for them to be vector fields, but I could have just paired them together into a tuple as well. 2 inputs, 2 outputs. Here I've got d inputs, I've got d outputs. Now, these 2 were actually examples of what I was calling basis transformations. So if we have a vector space, you can transform the basis of the vector space by a vector field. And so these are just 2 examples, but of course vector fields could be much broader than that. As long as the input is multidimensional and the output is multidimensional as a vector, they are vector fields. Now, gradients of scalar fields are vector fields. So if I go all the way back up to the scalar fields I introduced here, their gradients, which you all know how to compute, and we've computed them here, the gradients now have 2 inputs and they have 2 outputs, or in this case 3 inputs and 3 outputs. So gradients are going to, a gradient of a scalar field will give you a vector field. And what's interesting is that we can still jump higher and higher, and we can jump to matrix fields, where now I'm going to say that the domain is still, if it's a field, I'm talking about the domain as a subset of the vector space. But the codomain, the space of outputs, is now going to be matrices. So inputs are going to be vector spaces, outputs are going to be matrices. Input, a vector, output, a matrix. And we can look at some examples of that. So the Jacobian matrix, the first derivative of a vector field. So if we take a vector field from our previous examples, there's f. I've given it a boldface because it's a vector field, and I'm going to call all of its outputs f1 through fd, since we know there must be d of them. I can compute the Jacobian matrix, and I define it using the same gradient nabla. But some people will use a capital D or they'll use a J. This is going to be a matrix where we calculate partial x1 f1, partial x2 f1, partial xd f1, partial x1 f2, partial x2 f2, partial xd f2, and so on until we get to fd. So we're doing all combinations. The Jacobian of a vector field is all combinations of partial derivatives against vector field outputs. Right, so I d outputs, there are d possible partial derivatives, and so you end up with a d by d matrix. And because this matrix evolves or depends on the input in space, right? Depends on the choice of x1, x2, xd. Because it depends on that input, it's a matrix field, right? If I input it at 1, 1, 11, -5, or I input it at pi, -3, e, and 17, I'm going to get a different matrix out of it. So this is the point of a matrix field, is that we get a different matrix depending on the input. And we look at an example. So there's an example of a vector field. f of xy is x squared plus y squared plus x. I used this in the change of basis earlier. And we can compute its Jacobian as this is partial x of the first input. This is partial y of the first input. This is partial x of the second input. And this is partial y of the second input. And so that's how we compute the Jacobian. It should be familiar from Calculus 3, although you didn't call it a matrix field at the time, probably. The special thing now is that tensor fields are actually the generalization of all of this. Scalar fields are tensor fields, vector fields are tensor fields, matrix fields are tensor fields, and in fact we can increase the dimension of the output as many times as we want. We should notice, starting with scalar fields, the output was one-dimensional. In vector fields, the output was d-dimensional. In matrix fields, the output was d times d-dimensional, right? There was d in the left-right direction and d in the up-down direction. And so when we get to tensor fields, we can say, hey, I can actually increase that as much as I want. I can come up with n separate copies of a d-dimensional number. And so you actually get an n times d-dimensional object, which is most easily thought about as an array, right? The way that the matrix works is this is a d by d array, and then you could extend maybe after when you add a dimension to this matrix, you would extend forwards backwards into the page. It's now a d times d times d matrix, and so on. And so, sorry, this is not an nd dimensional object. It's a d to the n dimensional object, right? So a matrix is a d squared dimensional object. If I increase the matrix by a dimension of d, you get d times d array, which is d cube dimensional. So tensors, every time we decide to increase the degree of a tensor, we're going to take a new power of our dimension. And we're not going to get into like the super high dimensional tensors in this book at all, but it's good to comment on for what the rest of this chapter gets into, because we kind of need tensors to define a lot of the more important topics in the book, including the outer product. An example of tensor fields are in general relativity. This is the Einstein field equations, where each of these terms with the double subscripts, mu nu subscript, and mu nu subscript, those are actually tensor fields. So if you study general relativity, you should be fairly familiar with tensor fields. So this notation of tensor products is something you maybe did not run into in the past. I call this O times because it has an O around the times X. There's a big version, there's a small version. When we do this big version, we're thinking just like summation. This is actually considered R d1, little o times R d2, little o times ... little o times R dn. So I've taken, this is called a tensor product of vector spaces to create a tensor space, and then a tensor field is going to be a function who takes values in a tensor space. Now, the way we want to think about one of these tensors, as I mentioned, is as an array embedded in the n dimensions given here. Okay, so the width of the array, the width in the ith direction is given by this power di. There are n total directions. So this is the example in the matrix. If I have a 3 by 2 matrix, sorry, 2 by 3 matrix, it has 1, 2 total dimensions it exists in, right? I can write this in the two-dimensional plane of the board, but the width in the first dimension is 2. There's my width of 2. The width in the second dimension is 3, width of 3. So this is how we want to think about tensors, as just an array embedded in n dimensions where each of the directional lengths correspond to these powers. And I was already commenting on this. At the n equals 0 case, if I put a 0 up there, we actually just define this as r. So once I put a 0 there, we define it as r. But the rest of the numbers actually make sense. So when n equals 1, okay, I'm taking a tensor product from 1 to 1. That's just going to be r d1. That is exactly a vector space, right? And when I let n equal 2, this is now r d1 o times r d2. And so I'm allowed to take d1 cross d2 real values, which is a matrix of, I guess, width d2 and height d1, right? Because every entry here would be a real number. So when we have n equals 2, we've got the space of matrices. n equals 3, we have higher dimensional arrays. Now I have this remark here, it's within the remark, that I'm cautioning you not to necessarily attempt to visualize higher dimensional arrays. I really don't think it's necessary to get used to working with tensors. I say as the cognitive cost seems often not worth the intuitional gain. So trying to think about these as very high dimensional arrays I think is not the right choice. The right choice is to just be satisfied with the notation for what it is. We often will only encounter spaces up to n equals 2. Periodically we have to be okay with like 3 and 4, but we just have to be okay with that. We don't necessarily have to visualize it. Those are two separate actions we're allowed to take. So we're going to move on to inner, which I also call scalar, and outer, which I also call tensor products. And these are actions on vectors, right? You've used the inner product or the dot product before. So we're going to be thinking about vectors. So the inner product on vectors, I have a definition here, even though you've seen it before. If I take a vector and I decide to enumerate it, this is how I'm going to be enumerating vectors in this course. We want to think, what is, this vector u, which I just called ui, for I going from 1 to d. Why did I enumerate it like this? This is just a shorthand for me saying u1, u2, ... ud. So it's the d-dimensional vector. I just didn't want to write a giant amount of really tall vectors. If I'm in 28 dimensions, I'm not gonna use a 28-dimensional vector in the book. So this is how I'm going to notate vectors. It's just as their enumeration with the indexing I going from 1 to d. And we've got the same thing with v here. We can define the inner product. It's actually useful when we enumerate it, because the inner or the dot product or the scalar product, they all mean the same thing. It can be concisely notated with summation notation. The summation notation, when we have an enumeration of my vectors of a dot product, is just going to be the sum of the ith entry in u, the ith entry in v. If it's complex valued, I'm going to take a complex conjugate of v, and then I'm going to sum over every entry. This is exactly what you've done when you've taken inner products. So we'll go ahead and look at the example. So I look at the example. I'm calling u 1, 2, 3. I'm calling v -1, 0, -2. If I take their dot product, I'm taking 1 against -1. I'm taking 2 against 0. And I'm taking 3 against -2. And I'm adding those together. So the 1 against -1 is there and there. The 2 against 0 is there and there. The 3 against -2 is there and there. If you add all those together, you get -7. You can take u with itself, which is also known as the magnitude squared. And we get 1 times 1, because I'm just taking that by itself, 2 times 2, because it's that by itself, 3 times 3, and we add those together, we get 14. I do the same with v to get its magnitude squared. I'm doing 1 times 1, 0 times 0, -2 times -2, we get 5. So that's the inner product, and it's the kind that you've been very used to your whole life. But we're going to expand to the outer product, which, let's notice something special. Inner product takes 2 vectors and gives 1 scalar. So 2 vectors become 1 scalar. So we're getting smaller in tensor terms, because scalars have fewer dimensions than vectors. The outer product is going to be the opposite of this. So inner, things are getting smaller. Outer, they're going to get bigger. And I'm still going to be using this indexing notation on my vectors of u sub I and v sub I. And now I just define the outer product, which I'm going to call u. And if a v is complex valued, then I'll put a bar over v. But we're usually going to deal with real valued vectors, so it's not a big deal. You can call it just u and v, and we place them right next to each other without a dot. No dot. Or we can call it with the little O times tensor notation, u tensor v. And this is going to be the following object. Now I want to describe what this object is. What is that object? Well, let's think about how it's being indexed. This is why indexing is useful. How is it being indexed? It's indexed by I, it's indexed by j, and I and j start at 1 and they end up at d. So let's write out these indices. I have something like u1, u1, v1. I have u2, v2. I have u3, v3. But I also have something like u1, v2. I have something like u2, v1, and so on. And what if we used these subscripts to denote where we are in a matrix? So if we use the subscripts to denote where we are in a matrix, then we end up with the following. The outer product of two vectors u and v is a matrix. And how do we find the entries of the matrix? This is u1, v1. So I take the first entry of u, the first entry of v, and I multiply them together. This is u2, v3. So I'm taking the second entry of u, the third entry of v, because I'm looking at the row of the matrix and the column of the matrix, the row of the matrix and the column of the matrix. And that's going to define the matrix for me. So that's how you compute the outer product of two vectors. And if we simplified this, we'd get the following matrix. And I can do it with u against itself. We're just going to call that u squared. You can get the following matrix. These will always be symmetric. Actually, they'll always be positive and symmetric. Very useful. Always positive and symmetric. If you've taken linear algebra, you know what those mean. So it's always going to be a positive symmetric matrix. Same with, I guess I should say it's non-negative symmetric matrix, because you can certainly have zeros in there. But yeah, you can compute the outer product of vectors with themselves as the following. I've got to remark that we can technically define these products for all sorts of tensors. It won't be useful to think about it in the notation that I provide here. This is far too hideous for us to gain anything useful from. Unfortunately, if you're a differential geometry, you kind of have to rely on this notation, but we're not going to use that notation too often because it's really, really hideous. But what I would like to say is that the inner product can be defined on all tensors. It does not have to be defined just on vectors. Just because you used it on vectors when you were in Calc 3, we can actually use it on matrices. So let's grab two matrices here. Here's M, the following 3x3 matrix. Here's N, the following 3x3 matrix. We're going to take their scalar product, and it's everything you would expect. Just like with vectors, I'm looking at this and I'm multiplying by that. I'm looking at this and I'm multiplying by that. I'm looking at this and I'm multiplying by that. I'm looking at this, multiplying by that. I'm looking at this, I'm multiplying by that. Looking at this, multiplying by that. Looking at this, multiplying by that. Looking at this, multiplying by that. And looking at this and multiplying by that. And then I add everything together. So it's just the same as scalar products were with vectors. I'm just going to take every single term and add all 9 of them together, and I end up with -1. This is useful because we can contract tensors into scalars rather than just vectors into scalars. And we can do an outer tensor product of tensors as well, and this looks hideous as well when you do it in index notation. Now that's a lot of indexes. So we're going to try to avoid these when we can. Sometimes they're slightly unavoidable, but for the most part we're going to try to avoid them. But you can technically just build higher and higher order arrays from these outer products. Let's look at the outer tensor product of matrices. This is the only kind of non-trivial outer product of tensors that we can construct that's even a little bit visualizable. And so what I'm going to do with the outer product of matrices, instead of doing the scalar product, I'm going to do the same thing I did with vectors and allow this 1, 1 that's in my first matrix and 1, 1 that's in my second matrix to dictate the 1, 1, 1, 1 entry of my tensor product by multiplying them, and I recover a -2. I'm going to let the 1, 2 and the 1, 2 dictate the 1, 1, 1, 2 and multiply together to give me my tensor product out in that coordinate. 1, 2, 1, 1 gives me the tensor product out in that coordinate, and so on. And I repeat for all 16. Right, there's going to be 16 total cases because I can have a 1 or a 2 in either of 4 coordinates. So that's 4 squared, 16 total cases of interactions between these numbers. And I compute all 16 of them. And arguably, you could give yourself a nice 4x4 matrix. This is called the Kronecker product. But it's not as useful as a true tensor product is. The Kronecker product reduces me back to a matrix even though I've kept track of all of my 16 elements. The tensor product, unfortunately, let's think about the dimension of the array. What dimension is the array M tensor N in? Well, the first matrix was in 2 dimensions, right? So I can write it down in 2 dimensions. The second matrix is also in 2 dimensions. I can write that down. What is 2 times 2? 4 dimensions. So this is going to be an array in 4 dimensions. I'm going to do my best to describe what it looks like by using the 4-dimensional terms on the tesseract. Okay, so I'm going to compute the tesseract projection of the 4-dimensional hypercube. And I'm going to allow these indices 1, 1, 1, 1 to determine am I left or right, front or back, up or down, out or in. So the tesseract has this extra dimension of being out on the bigger cube or in on the smaller cube, on the inside of the cube. And so depending on these, so 2, 2, 1, 1, I would do right, back, up, out, and I would go over here, grab that -4, and put a -4 at that coordinate. And if I do that with my 16 numbers, we arrive at the following tesseract. Let's verify really quick with that -4 that I was right. So which one is that? That's here, 2, 2, 1, 1. So I'm going to be right, back, up, out. If I run down, I go to the right, I go to the back, I go to the upside, and this would be the up in, that's the up out, there's my -4. So this is the really a projection of the 4-dimensional hypercube. We call it the tesseract, and this is the array, the 4-dimensional array that we would have to represent tensor product of matrices as. So it's for this reason that I say you probably should not try to visualize these. This is, I spent some time creating this picture for you all. I would not go ahead and try to visualize these because, this notation actually tells us everything we need to know. So that tells us everything we need to know about the tensors. And so there's not really a reason to try to visualize it. The math speaks for us in some way. But if you really want to, you can study my tesseract and figure out how that works. So what is actually the point of all this? The only reason I decided I had to introduce all of this for you is because of the following: higher dimensional derivatives. Because you'll recall the gradient takes us from scalar fields to vector fields. And scalar fields, these are the solutions to PDEs. Those are solutions to PDEs. The gradient is a really important object in higher dimensions, and the output of the gradient is vector fields. What about the gradient squared? What sort of object is that? What about the gradient cubed? What sort of object is that? And so on. And we need to understand all of these. This is just the second derivative in higher dimensions. That's the third derivative in higher dimensions. You can't understand those without understanding tensors to a certain extent. And so that's why I had to introduce them here. I'm redefining the gradient, even though everybody's been using it so far this semester. You all know what the gradient is. And I give the gradient that you all know and love in the next remark. But I do technically define the gradient as the unique map, which maps, these are smooth functions from a vector space to a tensor space. So these are tensor fields. So it takes tensor fields and it maps them to tensor fields, smooth tensor fields to smooth tensor fields. But the degree of the tensor has increased by 1. This is why scalar fields go to vector fields. This is why vector fields go to matrix fields. This is why matrix fields would go to a higher order tensor if I compute the derivative of them, right? The derivative of a vector field is the Jacobian matrix, which is a matrix field. So you jump up in the order of tensors every time you compute a higher dimensional derivative. And so it's the unique map which performs that action, for which this is exactly the directional derivative, the one that you learned and knew and loved way back in Calc 3. It's for which the directional derivative can be computed on the tensor field phi, right? That's the directional derivative by definition with the limit quotient. And I'm saying, hey, that limit quotient needs to be the same as whatever we define the gradient as against the vector u. So that's the definition of the gradient. We can compare it with the reader's previous knowledge, all of your previous knowledges, and yes, it's exactly what you expect it to be. Now, this is something that only the differential geometries are going to care. It's because this is called a coordinate representation of the gradient, and it's with respect to the following two bases of the tangent space to a manifold. Okay, so once you assign a basis to your tangent space, then the gradient looks like the gradient that you all know and love. So you're totally allowed to use the gradient you all know and love, even though technically the earlier definition is the true definition. Now, what I have to say about this is that the gradient then generalizes to what you would expect in d dimensions. And if we want to look at powers of the gradient, then we can just by considering the tensor product of the gradient with itself. So back when I wrote something like gradient squared, this is really the tensor product of the gradient with itself. I write gradient cubed, this is the tensor product of the gradient vector with itself 3 times, and so on. So this is how we construct the powers of the gradient, and these are very useful operations for PDEs. There are some names for the gradient squared, by the way. It's called the Hessian matrix. And you can interpret it also as the Jacobian matrix of the vector field, which is the gradient itself. Now that vector field takes values in a differential operator space, so you have to be a little careful about what you mean by that. But Hessian matrix is a very safe way to talk about the gradient squared when we define it this way, as the outer product of the gradient with itself. Now, just to give you all an idea of what these look like, these higher powers of the gradient, you've probably encountered this before. The first gradient is its vector. The second power is the matrix of second derivatives, right? These are all mixed second derivatives. So it's a matrix which contains all mixed second powers of derivatives. Does anybody want to take a gander at the 3x3, or at the gradient cubed, the d by d array? It is the following. I spent a long time figuring out how to code that up so that it looked pretty. So we've extended now the matrix into 3 dimensions. And the entries in the 3 dimensions are all mixed third power derivatives, right? So I've got, hey, is 2 derivatives in x1 and 1 derivative in x2 a possibility? Yes, it is. It's right there. Is 1 derivative in xd, in the d direction, and 2 derivatives in x2 a possibility? Yes, it is. Is 1 in x2, 1 in x1, and 1 in xd a possibility? Yes, it is. So this contains all possible triples of third power derivatives in this d by d array. Okay, so this is where we're going to stop today. But the reason is that these higher powers of derivatives are very important, and so we have to understand what higher order tensors are and outer products to get to these higher order derivatives in large dimension. Anyway, that's all I've got. I know it's a pretty hard conceptual section because of higher dimensions than 3. Just kind of have to get used to it. I hope a lot of it made sense. We definitely have practice problems if you want to work on those. I'll see you in the next class. Bye.